Hi everyone. So in the last lecture, we were discussing byte ordering. This concept we were discussing. I can also say that concept of Endianness we were discussing. We have already seen what is little Endian architecture, big Endian architecture. Yes or no? So this concept of byte ordering, this actually we have seen. Now in this lecture, what we will do? We will do a lot of practice of these concepts. Okay, little Endian, big Endian, the concept of byte ordering. So basically a lot of practice we are going to do in this session. Okay, so let's start now. Before we do the practice, one small topic I want to teach you. Okay, see, in this byte ordering, I told you that we will study two topics. One is byte ordering for multi-byte data. Okay, if you have multi-byte data, for example 2 byte 4 byte data, integer data which is 4 byte, okay, long int which is 8 byte. So if you have multiple byte data, then for multiple byte data, how to do the byte ordering? Okay, yes or no? So this concept of little Endian, big Endian, this concept we have already seen for multi-byte data. Now we need to study this same concept, the concept of byte ordering, the same concept, little Endian, big Endian, the same concept we need to study for word. Okay. See, word is also multi-byte data. Yes or no? Agree? Okay. So you can simply say that these are actually same. These are actually basically same. Okay. Because word is also multiple byte data. Okay. So because what is a word? Word is nothing but your multi-byte data. So I can say that this is also multi-byte data. Correct? Yes or no? So I can say that these are actually same. So there is no difference. We have already seen little Endian, big Endian, these two concepts we have seen for multiple byte data. If you have multi-byte data, then how this byte ordering will work, this we have already seen. Now, in this lecture, we will study for word. Okay, this byte ordering for word. But you can see word is also multi-byte data. Yes or no? In a word, you can have, for example, maybe one word equal to 4 byte, one word equal to 8 byte, one word equal to 2 byte. Okay, yes or no? So word is also multi-byte data. So these are actually basically same. So there is no difference. Whatever concept you have seen for multi-byte data, the same concept you can apply for a word. Is this clear? Please tell me. Okay, so this is what we need to study, byte ordering within a word. Okay, if you have a word, then how to do the byte ordering within a word. So little Endian, big Endian concept for a word. This is what we need to study. Okay, so let's start. So let's assume that word size, I'm giving you the word size. Okay, so let's assume word size of CPU. Okay, because word size depends on the CPU. Yes or no? This size of word, that depends on the CPU. So let's assume that word size of CPU, that is 4 bytes. Okay, in one word you have, let's assume 4 bytes. Okay, is this clear? Now let's assume I am giving you some word. Okay, consider this word. So let's consider the word. Okay, I am giving you a word. Remember, one word equal to 4 bytes. So consider this word. Okay, so I'm giving you in the hexadecimal. I'm giving you what this means. Tell me this 0x. What this 0x means? This 0x simply represents hexadecimal. Okay, this represents hexadecimal. That the data I'm giving you in hexadecimal format. Okay, so I'm giving you this word. Consider this word, that is 0x. Let's assume, for example, A1, B2, C3, D4. Okay, so consider this word. Is this clear? Please tell me. Okay, so this is the word that is given to you, because you can see I'm assuming that word size is 4 bytes. So I'm giving you a 4 byte data. This 4 byte data I'm giving you. So tell me how many bytes are there in this word. How many bytes are there? So there are total 4 bytes, because remember, this is hexadecimal data. I'm giving you this in the hexadecimal format. So this 4 is actually nothing but 0, 1, 0, 0. Yes or no? This D, what is this? This is nothing but 0, 1, 1, 0, 1. Yes or no? Is this clear? Please tell me. Okay, so basically, actually, if you notice this word that is actually given to you, this word, if you notice, this is like this. In the hexadecimal format, you can write like this. And in the binary format, if you want to write in the binary format, then how you will write? So this A, this simply means 10. That means 1010. This is your A. What is B? What is 1? 1 means 0001. This is 1. What is B? B means 1011. Okay, this is B. What is 2? 2 means 0010. And what is C? C means 1100. Okay, this is C. And what is 3? 3 means 0011. Okay, What is D? D we have already seen, that is 1101. And what is 4? 4 is 010, 0100. Yes or no? So if you notice, this is your word. Okay. So consider this. This is your word, our word. Is this clear? Okay. So you can see this is the 4 byte data. Okay. Now tell me, if you want to store this word that is given to you, I want to store this word at the address 100. Okay. So let's store this word. This word I want to store. Let's store this word at location, at address, at memory location. Okay. Location means memory address. Location, what that means? That means memory address. Okay. And tell me, memory is byte addressable or word addressable? Tell me. The memory, that is byte addressable or word addressable? I told you that by default memory is byte addressable. Also, in the concept of this byte ordering concept, this comes into picture when you have byte addressable memory. Yes or no? This concept, byte ordering, this concept comes into play when you have byte addressable memory. So remember, your memory is byte addressable, means at any memory address you will find 1 byte. Okay. For every byte we give 1 memory address. So very simple. So store this word that you have, this word, or I can say the same word in the hexadecimal format. Okay. So this word we want to store at location, let's assume 0x100. Okay. So this address also I have given you in the hexadecimal format. Is this clear? Okay. This is your address. So this is our address. This is our address. So this address also I have given you in the hexadecimal format. Okay. So this I want to do, this word that you have, I want to store at this address. Now you tell me, if we follow big Endian architecture, then how your memory will look like? And if we follow little Endian architecture, then how the memory will look like? Tell me. In the little Endian, what will happen? In the big Endian, what will happen? So let's see first big Endian. Okay. In the big Endian system, what will happen? In the big Endian system, what will happen? Tell me. So you can see this is our data. This is our word. This is 4 byte data. So this is multi-byte data. Yes or no? Yes or no? So this is a multi-byte data. Okay. This 4 byte word. So this is nothing but your multi-byte data. Okay. So the same concept you can apply. This is your multi-byte data. Okay. So what I will do, very simple. This is your main memory. Let's assume this is the main memory. In the main memory, okay, and so on. So in the main memory, let's assume this is your address 100. Okay. These are the addresses. Okay. So these are the addresses in hexadecimal. Okay. All these addresses, these are given in hexadecimal, right? Okay. So these are the addresses in hexadecimal. Okay. So this 100, this is in the hexadecimal. Okay. This, let's assume 101, 102, 103, 104, and so on. Okay. And so on. Now, so how your memory will look like? Tell me. In the big Endian, if you are following the big Endian system, if your system is big Endian system, then you can see this word, how you will store this word in your main memory. This word, how it will be stored in the main memory? Very simple. Very simple, that basically these 4 locations will be used, because you are storing this word at the location 100, right? Yes or no? At this location you are storing this word, this 4 byte data, this 4 byte word you are storing at this location. What this means? That these 4 locations will be used. Here your word will be there. Okay. Yes or no? Here our word will be sitting here. Okay. 100, 101, 102, 103. In these 4 locations, our word will be sitting. Now, in big Endian system, what will happen? In big Endian system, you will start with the big end. Yes or no? What you will do? You will start with the big end. Okay. So now we need to see how to put the data here. So what we will do in the big Endian system, we will start with the big end. This big end we will start, big end. And what is the big end? So you can see big end means most significant byte. Okay. Yes or no? Okay. So start with the most significant byte, Okay. So let's start with the most significant byte. This is your most significant byte, right? Correct. Yes or no? This is the most significant byte. Okay. So let's start with this. So A1, then the next byte B2, then the next byte C3, then the next byte, that is D4. Is this clear? Please tell me. Yes or no? Okay. So very easy. So I can say this word you can store in the big Endian system like this. So your main memory will look like this. if I give you the photo of main memory, okay, then your main memory will look like this. Means at this 100, at this address, A1 will be there. At this address, B2 will be there. At this address, C3 will be there. At this address, D4 will be there. Okay, is this clear? Very simple. Now you tell me, so can I say in the big Endian, actually what will happen? In the big Endian, actually what will happen? Tell me. If you have big Endian system, in the big Endian system, what will happen? So this is your word. Word is 4 bytes, right? Okay, so in this word, basically, in this, let's see what will happen in the big Endian system. Okay, let's write the summary. Okay, so you tell me. So this is your word. Word is 4 bytes. There are 4 bytes in your word, right? Okay, so let's assume the 4 bytes are like this. Okay, in this word, there are 4 bytes. So let's assume the bytes are like this. So this is your byte 0, then your byte 1, then byte 2, then byte 3. Okay, is this clear? Okay, so let's assume these are the 4 bytes in your word. Okay, is this clear? So in the big Endian system, what will happen? Tell me. In the big Endian system, I can say that this most significant byte that will go to the lowest address. Okay, in the big Endian system, what will happen? In the big Endian system, tell me. So the most significant byte, MSB, what that means? That means most significant byte of the word. Most significant byte of the word. Byte of the word. Okay, your word is 4 byte. Remember, your word, that is actually 4 byte. There are 4 bytes in your word. Okay, so there are 4 bytes. There is, I can say, okay, or maybe ABCD, something like that I can say. Okay, so let's assume there are 4 bytes. Let's assume A, B, C, D, something like this. Okay, so let's assume this is 1 byte of data. Okay, just consider this is 1 byte. Just assume this is 1 byte. You can say X, Y, Z, W. Okay, for simplicity, so that you don't get confused with the hexadecimal notation. So let's assume this is your X, Y, Z, W. This is your word. Okay, this is your word. So this is a 4 byte data. So now in this big Endian system, what will happen? The most significant byte of the word. What is the most significant byte of this word? In this word, what is the most significant byte? This is the most significant byte of this word. Of this word. So you can see most significant byte of word that will go where? That will be stored where? That will be stored at lowest address. Yes or no? That will be stored at lowest memory address. Okay, is this clear? Please tell me. Okay, very simple. Okay, so this basically you will start with the most significant byte. Okay, you will start with the big end. The name itself is telling you that you will start with the big end. You will start with the big end. Okay, so the most significant byte of the word, this most significant byte of the word, this you will put where? You will put, you will store it at the lowest memory address. Okay, very simple point. Now, what will happen in the little Endian system? Tell me. If you are using little Endian system, if you are using little Endian system, little Endian architecture, if you are using little Endian architecture, then what will happen? In the little Endian architecture, tell me how the memory will look like. So these are the addresses. So you can see we are storing this word at this address. So these 4 locations will be used. Here our word will be there. Our word you will put here. Okay, is this clear? Very simple. So in the little Endian architecture, what will happen? You will start with the little end. You will start with the little end. Little end means least significant byte. Least significant byte. Okay, yes or no? Least significant byte of the word. Byte of the word. Okay, so you will start with the little end. So this is the little end. You can see this is the least significant byte of this word. Okay, so what you will do, you will start with this. Means first you will at this address. Okay, at this lowest address, what you will put? At this address you will put D4, then the next byte C3, then the next byte, that is B2, and then the next byte, that is A1. So this is how your main memory will look like in the little Endian. Okay, in the little Endian, this is how your main memory will look like. Is this clear? Please tell me. So if you have a word that is 4 byte, let's assume your word is like this. Your word is like this, X, Y, Z, W. Okay, this is your word. Then in the little Endian, what will happen? In the little Endian system, okay, because your word is multi-byte data. Okay, in your word, You can see this is your word, that is 4 byte. So this is our word. I can say this is our word. Okay. And this is multi-byte data. Now, so in the little endian system, what you will do? Where this? So you will start with the little end. Little end means least significant byte. And what is the least significant byte in this word? In this word, what is the least significant byte? So you can see W. This is the least significant byte of this word. Correct? Yes or no? Okay. So of this word, this is the least significant byte. So you will start with the least significant byte, and this least significant byte, this will go to the lowest address. This will go to the lowest memory address. Okay. So very simple point. And this B means byte, least significant byte of the word. Okay. Is this clear? So I can say this least significant byte of word, this will be stored at lowest memory address. So that's it. So this is your topic. Okay. So you can read here. Okay. Just read this. The name big endian, when you use this word, the name big endian is used when lower byte address is used for most significant byte of the word. Just read this line. We have already seen this. Little endian, big endian, we have already seen this. Now tell me, did you understand this statement? Read this statement. The name big endian is used when lower byte address, means lowest byte address, is used for most significant byte of the word. Is this clear? Please tell me. This statement, is this clear? So you can see what is big endian. Big endian means the lowest byte address that is used for most significant byte of the word. Similarly, when you can say little endian means what? Little endian means, little endian means that lowest byte address is used for least significant byte of the word. Okay. So very simple. So this is the point. I hope you understood. Okay. You already know what is least significant byte and what is most significant byte. These things you already know. Okay. Now let's move on now. So you can see, if this is your word, so how should you, okay, so this is the concept, byte ordering. This is the concept. How should bytes within a word, okay, if I give you a word, then how should the bytes within a word be ordered in the main memory? Okay. So you can see, if I give you a 32-bit word, this word, if I give you, then how you will store it? Very simple. In the big endian, you will start with the big end. Okay. You will start with the big end. So you will store like this. And in the little endian, you will start with the little end. You will start with the least significant byte. Okay. So you will start with the least significant byte. So you can store like this. Okay. So very simple. So this concept we have seen. Now let's move on now. Okay. So let's see. Now we will do a lot of practice. We are going to do for this topic, endianness, little endian, big endian. A lot of practice we will do. So can you take your copy pen? Now, can you notice what I've written here? All practice questions on byte ordering. What that means? Can anyone tell me what this means? I'm saying all practice questions. All practice questions. So let me tell you that on the internet, in the standard resources, whatever question I found, I have put here. You will see. We will see Washington University question, GATE question, ISRO question. Basically, we will see every question available. I can say every GATE relevant question from this byte ordering we will study. Okay, we will solve. So take your copy pen and let's solve all practice questions on byte ordering, means little endian, big endian. Okay, let's solve some questions. Okay, so let's start. Now, this is Washington University question on byte ordering, means this is based on the concept of little endian, big endian. Little endian, big endian. So this question, let's solve. Now, so you can see this is Washington University question for 20 points. Let's solve this question. You have 32-bit integers. So 32-bit integers means how many bytes are there? Tell me. 32-bit integers means 4 byte. Yes or no? So this is your multi-byte data, right? Okay. You have 32-bit integer. That simply means that this is your multi-byte data. And when you multi-byte data, then you tell me, when you multi-byte data, then endianness will come into picture. Yes or no? Whenever you have multi-byte data, so you have 4 byte data. If you notice, this is your 4 byte integers. So there are 4 bytes. Okay. And whenever you have multi-byte data, then how to store this data in the main memory? For that, the concept of byte ordering comes into picture. Okay. So let's solve it. Now, you can see here, what is the first question? The first question is, write the decimal number 13 in binary as a 32-bit big Endian integer. Okay, so what we need to do? We need to write decimal number 13 in binary as a 32-bit big Endian integer. This is what we need to write. Okay, but read this statement. Read this statement. What this statement is telling you? Tell me what this statement is telling you, that whenever you are writing your answer, when you are writing your answer, then make sure that you put the byte with the lowest address on the left. Okay, whenever you are writing your answer, then make sure that you put the byte with the lowest address on the left and byte with the highest address on the right. What this line means, can anyone tell me? Okay, first you understand this line. First understand this line, what this means. Okay, what it means. What this line means. See, this line simply means that, let's assume that somehow, okay, I don't know which architecture, but let's assume that your memory looks like this. Okay, just for a moment, let's assume that your main memory looks like this. These are the addresses. Okay, and I am saying that let's assume your main memory looks like this. For example, 1, 2, A, B. Okay, for example, maybe 2, C, and D, E. Okay, so let's assume this is your main memory. If your memory looks like this, if memory looks like this, then what your answer will be? If memory looks like this in some Endianness, okay, in some Endianness, is this clear? Okay, so if your main memory looks like this, I don't know little Endian or big Endian, I don't know little Endian or big Endian. I'm saying if your memory looks like this, okay, in any Endianness, then your answer will be what? Then write your answer. So how you will write your answer? Then you write your answer like this. Okay, like this. So you can see how to write the answer. See here, this statement is already telling you. See, when you are writing your answer, read this statement. When you are writing your answer, make sure that you put the byte with the lowest address on the left. Okay, this is the byte with the lowest address, yes or no? So you put this on the left, and then AB, then 2C, and then DE. Is this understood? Please tell me. Okay, so if your main memory looks like this in some Endianness, I don't know which Endianness, okay, big Endian, little Endian, whatever Endianness you take, if your main memory looks like this, then write your answer like this. Is this clear? Please tell me. Did you understand this statement? This statement, did you understand in this question, in this Washington University question, this statement, did you understand? Okay, so very simple statement that when you are writing your final answer, then make sure that byte with the lowest address you write on the left. Okay, whether you take little Endian, big Endian, does not matter. When you are writing your final answer, then make sure that you put the byte with the lowest address on the left. Okay, your final answer should look like this. If your memory looks like this, okay, if your main memory looks like this, then your answer should look like this. So this is the point. Okay, now let's solve this question. Now let's see what the part 1. So tell me, what is the answer for part 1? Write the decimal number 13. We need to write the decimal number 13 in binary as a 32-bit long int. Okay, so first of all, you tell me this number you have 30. This is your data, right? Can I say that our data, that is nothing but 13? So we need to write this data as a 32-bit big Endian. Okay, you can see we need to write this as a 32-bit big Endian integer. So first you convert this into binary. So tell me what your binary will be. So first you convert this into 32-bit binary. 32-bit binary. So what your data will look like? Because ultimately we want 32-bit, right? In all the questions, we want 32-bit, 32-bit, 32-bit. Okay, so first you convert this 13 into 32-bit. Let's do that. So tell me, in the 32-bit, how this 13 will look like for 32-bit? Very simple. This 13 is actually, if you notice, this 13 actually nothing but 1101, right? Okay, but we want 32 bits. So just put zeros, just put extra zeros. So actually it will look like this, 1101. Okay, just put extra zeros. How many extra zeros I need to put? how many leading zeros I need to put? Tell me. So total 28 leading zeros I need to put. Yes or no? Okay. Leading zeros, do they affect the number? Do they affect the number? The leading zeros, they will not affect the number, right? Because you already know, for example, if I put like 032, that is same as 32. Okay. So these two things are same. You already know. Okay. These two things. So leading zero does not matter. Okay. These zeros, they do not matter. So you can put extra zeros. So what you can do, you can put 28 extra zeros you need to put. Okay. So let's put. So 8, then next 8, then next 8, and I think 4 more I need to put. Okay. So 4 more zeros we need to put. And then finally, our data will be 1101. Okay. So this is your data. Yes or no? This is our data. This is our data. I can say that this is the data that we have. Okay. If you want, you can convert it into the hexadecimal also, but that is another question, right? Yes or no? See, part B is for hexadecimal. Okay. You can see that is another question. So let's solve these two questions first. Then we will solve little endian. First, we will solve big endian. You can see part A, that is talking about big endian in binary. Okay. What is part A? Part A is big endian in binary. In binary, the part B is saying big endian, but consider the hexadecimal representation. The part C is telling little endian binary, and part D is saying little endian hexadecimal. Okay. So let's solve this question now. So first you tell me, now what will happen in 32-bit in big endian system? In big endian system, what will happen? Tell me. In big endian system, in the big endian system, what you will do? You will start with the big end. Yes or no? Okay. In the big endian system, if you notice, you will start with the big end. This is the big end. This is the big end. What big end means? Big end means most significant byte. This is most significant byte. Okay. So what you will do? You will start with the most significant byte. Okay. So in the big endian, actually the answer will look like this. In the big endian. Okay. If you are storing at address, at some address, at any address, does not matter. Okay. Whatever address you take. So in the big endian, actually you will start with the big end. Okay. So first you will put this most significant byte. Here you will put the most significant byte. This most significant byte you will put here. Then what you will do? Then the next byte, then the next byte, then the next byte, and so on. So tell me, can you notice your final answer? What that will be? That will be same as this number. Okay. Because I told you in the question, it is saying that if your photo looks like this, if your main memory looks like this, then write your answer like this. Okay. Yes or no? If your main memory looks like this, then write your answer in this order. Write your answer in this order. So if you notice in the big endian system, how the main memory will look like? You can see this is the main memory that will look like, because you will start with the big end. So first you will put most significant byte, then the next byte, then the next byte. Okay. What is the next byte? That is like this. Okay. And what is the next byte? That is like this. Okay. So finally tell me, if your main memory looks like this, then your final answer will be what? Then your final answer will be what? Then final answer for option A, for part A. Tell me what your answer will be. If your main memory looks like this, then what you will do? Your final answer you need to put in this order. Okay. Yes or no? First you need to put the byte at the lowest address. The question is already saying that when you are writing your answer, then put the byte with the lowest address on the left. Okay. Put the byte with the lowest address on the left. So what you need to do here? Your final answer will be, first you will put this byte, then you will put this byte, then you will put this byte, then you will put this byte. Okay. So basically the same answer you will get. Agree? Yes or no? So your final answer will be same as this. Your final answer will be like this. This is your final answer. I am writing the final answer. Okay. So this is your final answer. Is this clear? Please tell me. Did you understand? Let me know. This is your final answer. Please tell me, did you understand this? This question, did you understand? Okay, because this is our data. See, our data is already there. Okay, our data is 13. So first what you do, you convert it into 32-bit binary. This is our data. This is our data. In the big Endian system, how you will represent this data, how you will put in the main memory. In the big Endian system, this data you have, how you will put this data in the main memory? Very simple. You will start with the big end. Okay, so you will start with the most significant byte. So first you will put this most significant byte at the lowest address, then the next byte, okay, and then the next byte, and then finally this least significant byte at the highest address. Okay, and once you have this answer, once you have this photo, then how to write the answer? Very simple. Okay, start with the lowest address. Okay, start with the byte with the lowest address, put this on the left, put this on the right. Okay, so your final answer will be this. That's it. Now tell me the answer for part B. Tell me the answer for part B. Let me know. For part B, what I need to do, or before that, just tell me for part C. Okay, let's do the answer for part C. In part C, what we have? We have little endian. Let's see the answer for part C, little endian binary. This is your part C, if you notice. Okay, so 32-bit little endian binary. Okay, binary. Now you tell me the answer will be what? So in the little endian, how the main memory will look like? Anyone? In the little endian, if you are storing this data at address 100, let's assume I am storing this data. This data I am storing at address 100, means from 100 to 103. In the little endian, what will happen? Very simple. You will start with the little end. Yes or no? You will start with the little end. This little end you will put here. Okay, so you will put the little end. This is your least significant byte. This is the least significant byte. This is the little end. So you will start with the least significant byte. You will put it or at the lowest address. Okay, so you will put this byte first. First you will put this byte. That's it. And then the next byte. Then what you will do? Then this next byte you will put at this address. Okay, so you can see. Then the next byte. Then the next byte. And tell me your final answer, how you will write. So your final answer, how to write that? Let me know. This is already given in the question that your final answer, you have to write that byte at the lowest address. You have to write on the left. Okay, so your final answer for this part C, what that will be? That will be you start with this. Okay, so just write like this. This is your little endian. You can see one thing. Basically, you are starting with the little end. In the little endian, what you are doing? You are starting with the little end. This is your little end. You are starting with the little end. In the little endian, what you are doing? Tell me. You are starting with the little end. This is the little end, right? Yes or no? Okay. Then what you do? Then the next byte. Then the next byte. Then the next byte. Okay. So this is your final answer. I hope you understood. Okay. What is the part B? In the part B, we need to convert it into hexadecimal. Read the part B. Write the decimal number 13 in hexadecimal. Okay, as a 32-bit big endian. So first you convert this into this data, this binary data that you have. First you convert into hexadecimal. So what that will be? In the hexadecimal, what it will be? It will be like this. Okay, this is your 0, 0, and so on. So in the hexadecimal, this will be like this. Okay, finally it will be 0 and this will be D. Okay, yes or no? So this is your hexadecimal. Now tell me, part B, the answer for part B. So in the big endian, what will happen? In big endian, what your final answer will be? In the big endian system, your final answer will be very simple. You start with the big end. You start with the big end. This is the big end. You start with the big end. That's it. Okay. So in the big end, okay, your final answer, I'm writing the final answer directly. Okay. So your final answer will be what? You start with the big end, then the next byte, then the next byte, and then the next byte. So this will be your answer. Is this clear? So this is going to be your answer. Simple, right? Yes or no? Very simple. Now tell me the next. What about part D? Part D means little endian. Tell me about this. In the little endian, what you will do? You will start with the little end. This is the little end. Correct? Yes or no? This is the little end. So you will start with the little end. Okay, so first you put this byte, then the next byte, then the next byte, then the next byte. This will be your answer. Okay. So quite simple, right? Okay, hexadecimal. This is in the hexadecimal. So just put it here that this is the answer is also in the hexadecimal. Okay, understood? Now let's move on. Is this clear? Please tell me. This particular question, is this understood? Let me know. Now let's see the next question. This is another question from the Washington University, and this is a nice question. Let's solve this. What this question is saying. For each of the following, answer same if the little endian and big endian representation are same. Okay, so some options are given to you, and for each of them, what we need to do? We need to answer same if little endian and big endian representations are same. Okay, and if little endian, big endian representation are different, then answer different. Okay, all the numbers are 32-bit integers. All the numbers are multi-byte data. Yes or no? Did you understand the question? A very nice question. This is a beautiful question. Okay, from Washington University. This is a standard question. This is actually a very nice question. So let's solve it. So you can see all the numbers are 32-bit integers. All the numbers, these are multi-byte integers. Okay, now let's solve it. So tell me, the maximum unsigned number, what is that? In 32-bit, what is the maximum unsigned number? Let's solve the first one. Let's see the first one. First of all, you tell me, in 32 bits, what is the maximum? Maximum means largest. What is the largest unsigned number that you can create? Unsigned integer. Tell me, what is the largest unsigned number you can create? Anyone? If you want to create maximum unsigned number, then in binary, how it will look like? It will be all ones. Yes or no? In 32 bits, there are 32 bits. I want to create maximum unsigned number. I want to create. There is no sign. So what I will do? I will simply put all ones. Okay, yes or no? So your number actually will be all ones. Just put all ones. Just put all ones. So if you notice, your number is this. This is the maximum unsigned number. Okay, just put all the ones. Is this clear? Please tell me, did you understand this? See, the question is saying the maximum unsigned number in 32 bits. In 32 bits, if I want unsigned number, okay, there is no sign. So I can say if I want maximum unsigned number, then I will put all ones. That is same as what? That is same as FF, 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 FF in hexadecimal. In hexadecimal, you can write like this. Okay, in the hexadecimal, because this is nothing but F in hexadecimal. Correct? Is this clear? So this is your largest unsigned number. Now you tell me, for this number, can I say little endian system, big endian system, they will be same? Yes or no? Can I say that big endian and little endian representation will be same for this? Yes, of course. Yes or no? For this little endian, big endian will be same. Okay, so I can say for this number. Okay, for this number, what I can say? I can simply say that little endian, big endian will be same. Little endian and big endian representations are same. Representations are same. Okay, why? What are the reason? What are the reason? Tell me. Because you can see in the little endian, you will start with the little end. Okay. In the little endian, what you will do? You will start with the little end. You will start with this. In the little endian, you will start with the little end. But all are FFFF. Okay, yes or no? All are FFFF. So in the little endian, you will start with the little end. In the big endian, you will start with the big end. But all are same. All are 1, 1, 1, 1, 1, 1. All are FFFF. Okay, so very simple. So this is the simple point that, okay, in the big endian, what you will do? In the big endian, you will start with the big end. You will start with the big end. So that's it. FF, 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 and so on. So this is your answer. So for this question, the answer will be what? For this question, what I will say? I will say same. Little endian, big endian, both representations are same. What about the answer for the next? The maximum. Sorry, actually, we have done the second part, right? We have done the maximum unsigned number we have done. Okay. We have done the part 2. We have actually done the part 2 because we have done maximum unsigned number. Okay. Is this clear? The part 2 we have done. We have done part 2. Now let's do the part 1. Okay. So this part 2 is done. This is done. Remember, we have done the part 2. That is maximum unsigned number. What about minimum unsigned number? Tell me about the minimum unsigned number. What about the part 1? In 32 bits, 32 bits minimum unsigned number. If you want unsigned number which is minimum, that is 0. Yes or no? Minimum unsigned number I want minimum unsigned number. Okay. So if I want minimum unsigned number, then very simple, that is 0. That is all zeros. So in 32 bits, minimum unsigned number will be all zeros. All zeros. Correct. Okay. So if you notice the minimum unsigned number, that will be basically, that will be in hexadecimal. If I write in hexadecimal, it will be 00 00 00 00. Correct. Yes or no? Now you can see for this, can I say little endian, big endian will be same? Little endian equal to same as big endian. Yes or no? Is this clear? Okay. Little endian, big endian will be same. In the little endian, you will start with the little end. In the big endian, you will start with the big end. But all are zeros. So there is no change. So I can say for this also they will be same. What about the third one? +1 in 2's complement. Okay. So tell me what is +1 in 2's complement? Let's see the third part. +1 in 2's complement. In 2's complement. This 2's complement, 1's complement, this concept we have already seen in the digital logic. Okay. What is 2's complement? What is 1's complement? These concepts we have seen in the digital logic. So +1 in 2's complement and 32 bits. Okay. 32 bits. So tell me what that will be in binary, how it will look like. +1 in 2's complement. Okay. For positive numbers, 2's complement is same as sign magnitude system. Yes or no? If you have a positive number, for positive number, 2's complement is same as your sign magnitude system. Okay. So how your +1 will look like? Very simple. All zeros ending with 1. Okay. So your +1, your data is actually like this. In hexadecimal, if I write, that will be all zeros. All zeros. Okay. And finally, at the end, there will be 1. In binary, if I write, if you want, you can write in the binary also. In the binary, it will be like this. All zeros. There will be all zeros. And then finally, this will be 1. Okay. So you can see this is actually 1. This is actually your 1. Okay. So understood? Simple. Okay. So in the hexadecimal, you can write, or you can write in binary. Now you tell me for this number. Okay. Focus on this number. For this number, you tell me little endian, big endian, will they be same? Will they be same? Little endian, big endian. How the little endian will look like for this number? How the little endian will look like? Tell me. In the little endian, what you will do? You will start with the little end. Okay. You will start with the little end. So in the little endian, what you will do? You will start with the little end. And then the next byte, then the next byte, then the next byte. This is your little endian. In the big endian, what you will do? In the big endian, you will start with the big end. In the big endian, you will start with the big end. Okay. So simple. So they are different. Clear? Please tell me, did you understand? Let me know. Remember, in the little endian, you will start with the little end. In the big endian, you will start with the big end. Okay. So you can clearly see they are different. Okay. This and this, they are different. So I can say for this question, the answer will be different. What about the next one? Anyone? -1 in 2's complement. What is -1 in 2's complement? Tell me. Anyone? What is -1 in 2's complement? Okay. So this is your part 4. -1 in 2's complement. (32 bits). In 32 bits. Okay. So you first, what you will do? If you want -1 in 2's complement, then first what you will do? Tell me first what you will do. First you will write plus 1 in 2's complement. Okay, so just see plus 1 in 2's complement. What that will be? Plus 1 in 2's complement. That will be all 0 ending with 1. Yes or no? That will be like this. All zeros and ending with 1. Yes or no? So this will be your plus 1. Now tell me how to find minus 1 in 2's complement. How to find that? Minus 1 in 2's complement. We have already seen this. Okay, from left to right you go till the first one. Till the first one you write as it is. Then everything you will complement. Yes or no? Then everything you will complement. Is this clear? Till the first one as it is. See, go from left to right. Go from left to right till the first one as it is. Till the first one as it is. Okay, but then complement everything. But then you what you do? You complement everything. Now you complement everything. Okay, so you can see minus 1 in 2's complement, that is actually all ones. Is this clear? See what I'm saying. If you want, for example, let's assume I want let's assume that I want minus 4 in 2's complement. Okay, I want minus 4 in 2's complement. Okay, let's assume that in 8 bits. Then tell me what your answer will be. If I want minus 4 in 2's complement, then what you can do? First, you can put plus 4 in 2's complement. Okay, first what you do, you write plus 4 in 2's complement. So plus 4 in 2's complement, that is same as sign magnitude. For positive numbers, 2's complement is same as sign magnitude. Okay, so because this is a positive number, so 2's complement representation will be same as sign magnitude. Okay, so what that will be? That will be 0 0 0 0 1 0 0. Yes or no? Now how to write minus 4 in 2's complement? How to write that? Very simple. Go from left to right. Go from left to right. Okay, till the first one you go. Go from left to right. Go from left to right till the first one you go. Till the first one. That will be same. Till the first one, everything is same. Okay, till the first one. Till the first one, everything will be same. Till the first one. Till the first one, everything will be same. After that, everything will be complement. Okay, after that, everything will complement. So this is your minus 4 in 2's complement. Is this understood? Please tell me. Okay, so very simple. So here you can notice minus 1 in 2's complement, that will be what? Minus 1 in 2's complement, that will be all ones. Okay, that will be nothing but all ones. 1 1 1 1 1 1 and so on. 1 1 1 1. Okay, 32 bits in 32 bits. So this is your minus 1 in 2's complement. In hexadecimal, if you write, you can write in the hexadecimal also. So that will be FF, 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 FF. Yes or no? Is this clear? Please tell me. Now tell me, for this, can I say little endian, big endian will be same? Little endian, big endian will be same, right? Yes or no? For this, little endian, big endian, they will be same. So this is your answer for the part 4. Okay, so for this question, answer will be that little endian representation, big endian representation will be same. What about the next one? Quickly tell me. Tell me the answer for the next one. The maximum 2's complement number. The maximum 2's complement number. Okay, I want maximum 2's complement number. Tell me, what is maximum 2's complement number? Part 5. In 32 bits. In 32 bits, what is maximum 2's complement number? Anyone? See, maximum 2's complement number will be positive. Yes or no? Agree? Maximum 2's complement number. I want maximum 2's complement number in 32 bits. So that will be a positive number. Agree with me? I want maximum 2's complement number. So that will be positive. Okay. So what you can do in 32 bits, if I want maximum 2's complement number, then that will be positive. That you already know. Yes or no? It will be positive. It will be positive. Correct. Okay. So for positive numbers, can I say 2's complement and sign magnitude, they are same or not? Tell me. For positive numbers, 2's complement and sign magnitude are same or not? Okay, for positive numbers, 2's complement representation is same as sign magnitude. Sign magnitude representation. Correct? Is this clear? Okay, so what to do? If I want maximum 2's complement number, then what I will do? Did you understand this logic? See, I want maximum 2's complement number. So I know that that number will be positive. I already know that number will be positive. And for positive numbers, 2's complement is same as sign magnitude. Sign magnitude representation and 2's complement, they are same. But for positive numbers, so the sign bit will be 0. Yes or no? Sign bit will be 0. For positive numbers, I can say that sign bit, that must be 0. Sign bit must be 0. Okay, so just put sign bit equal to 0. Now I want maximum. So just put all ones. Yes or no? Is this clear? Please tell me. Now just put all ones. This is your maximum 2's complement number. Is this understood? Please tell me. Did you understand this? In 32 bits, this is the maximum 2's complement number. Okay, just this will be 0. The remaining all will be ones. Okay, now you tell me in the hexadecimal what I can write. The same number in the hexadecimal. In the hexadecimal, I can write it that this is your basically 7. Okay, this is 7, right? This is 7 in hexadecimal. This will be 7 in hexadecimal. Okay, so 7 and then FF. Yes or no? So now tell me, this will be same in the little endian, big endian. Will it be same? What it will be in the little endian? You just tell me in the little endian what it will be. This is your number in the little endian. How it will look like? Very simple. In the little endian, you will start with the little end. In the little endian, you will start with the little end. So just start with the little end. So in the little endian, it will look like this: FF, 7F. In the big endian, how it will look like? In the big endian, start with the big end. Start with the big end. So it will look like 7F, FF. Okay. So are they same or different? Are they same or different? They are different. Okay. So for this question, the answer will be what? Tell me. For this question, the answer will be different. See, this question is beautiful, right? I can guarantee that many students will make mistake in this question. Actually, in this question, multiple concepts are used: little endian, big endian, and number system, sign magnitude, 2's complement, 1's complement. So multiple concepts are used in this question. So this will be a very nice question. If this type of question comes in the GATE exam, MSQ question, then that will be very nice question. Okay, so you can see. So very nice question from Washington University. Now let's just do the last one also. Tell me, what about the answer for sixth one? The minimum means most negative 2's complement sign number. The minimum most negative 2's complement sign number. Now tell me the answer for this one. What is the minimum 2's complement sign number? The answer for sixth one. In 32 bits. In 32 bits, what are the minimum? What are the minimum 2's complement? What is the minimum 2's complement number? Tell me. What are the minimum 2's complement number? This is what I want. So if I want minimum 2's complement number, this we have seen in the digital logic. I told you in the digital logic how to create minimum 2's complement number. What to do? Very simple. First of all, just put the sign bit equal to 1 and the remaining will be 0. The remaining all, they will be 0. Yes or no? The remaining all will be zeros. Do you remember this? Do you remember this? This we have seen in the digital logic. In the digital logic, we have already seen this. Okay, most of the students, they have given correct answer. I can see all of them have given correct answer. Very good, very good. Okay, so you can see in 32 bits, I want minimum 2's complement number. So what I can do? So that will be, start with the sign bit will be 1, okay, and the remaining will be 0. This will be your minimum 2's complement number. Okay, so in the hexadecimal, what I can write it? In the hexadecimal, what it will be? It will be 8. In the hexadecimal, it will be 8, then 00000000. Okay, this will be your number. Now you tell me, in little endian, what it will be? This number in little endian and this number in big endian. How it will look like? This number, how it will be stored in the little endian? If you store this number in a little endian system, then what will happen? Very simple. In the little endian system, you will start with the little end. You will start with the little end. So your answer will be, you will start with the little end. Okay. In the big endian system, you will start with the big end. Are they same? They are not same. They are not same. They are different. Okay. So very simple. So for this question, the answer will be different. Okay. So that's it. So this is a very nice question we have done. This question number E, we have done it. Okay. Did you understand? Please tell me. Did you understand this question? Very nice question. Multiple concepts are used. Did you understand? Please tell me. Let me know. Now let's see the next one. The question number F. Give in hexadecimal. Okay. Give in hexadecimal a 32-bit value that represents the same unsigned number. Okay. That represents same unsigned number in big endian or little endian is not one of the previous problem. Basically, other than these, give a 32-bit value. You give me a 32-bit value that represents same unsigned number in big endian also, in the little endian also. In the big endian, in the little endian, that will represent same unsigned number. So tell me, what will be the answer for part F? Anyone? Anyone want to give? Satyam has given A, B, A, B, A, B, A, B. Yeah, that will work. That will work. Okay, so Satyam has already given this. So for part F, Satyam has given this answer. A, in the hexadecimal, he has given A, B, A, B, A, B, A, B. Okay, now you can see that, okay, this number, this is a 32-bit value, first of all. This is a 32-bit value. Okay, and you can see in the little endian, in the big endian, it will represent the same unsigned number, right? Yes or no? In little endian, in big endian, this will represent the same unsigned number. In the little endian, what it will be? This is your 32-bit value. Okay. Now, this 32-bit value, you can see what the question is saying. Read the question. Give in hexadecimal a 32-bit value that represents same unsigned number in big endian, little endian. Okay. So you can see that. Look at this value. This is the 32-bit value. Okay. And in the little endian, in the big endian, this will represent the same unsigned number, because in the little endian also, this will be what? This will be AB, 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 AB. Okay. Because in the little endian, you will start with the little end. Okay. In the big endian, you will start with the big end. So in the little endian, in the big endian, in both of them, this will represent the same unsigned value. You can see this is same as this. Okay. They are same. Correct. Yes or no? So you can notice they are same. Now, Devans has given FF0000FF. That is also correct. Okay. So this answer is correct. Another alternative answer. Another answer. Devans has given another answer, that is FF in the hexadecimal, FF0000FF. Yeah, this is also correct. Okay, this. So can anyone tell me general answer? Can anyone tell me general answer? Anyone want to tell me the general answer? Like, give me something generalized answer. Basically, in the generalized answer, in the hexadecimal, you tell me, I can simply say that the first byte must be same as the last byte. Yes or no? Do you agree? Basically, this byte, okay, just consider what I'm saying. Basically, this byte must be same as this byte, and what should happen? This byte must be same as this byte, right? Do you agree? Please tell me. And this byte must be same as this byte. Okay, here where this is a byte, okay, this is a byte. Is this understood? Please tell me. Do you agree? Yes or no? This is the general answer, right? Okay, this byte must be same as this byte, and this byte must be same as this byte. Now you can see this is a 32-bit value. In the little endian, in the big endian, this will represent the same unsigned value. Yes or no? Is this clear? So this is your general answer. for this question. Okay, so that's it. You can see here the answer is already available in this Washington University, this midterm. This is a midterm question, answer is available. Many answers are available. For example, FF0000FF. Basically, what should happen? That this byte must be same, this byte must be same. Yes or no? This is already given. The general answer is already given here. You can read this. Okay, so that's it. So we have done all the Washington University questions. Please tell me, did you like these questions? Let me know. We have done all the Washington University questions we have done. Okay, you can see all of them we have done. Please tell me, did you understand? Let me know. Now let's move on now. Tell me the answer for this question. This is a question from University of New Hampshire. You can see University of New Hampshire question on Endianness. And this is a very beautiful question. Let's solve it. You tell me the answer. Read the question carefully and tell me the answer. This is a beautiful standard question. I want correct answer from you. Read the question and tell me the answer. How would the following C string null terminated? This string is given to you that is null terminated. Okay, a C string that is given to you. Okay, so this is the C string that is null terminated. So what is this string? Tell me. Anyone? What is this string? In C language, what is this string? This string is basically X, Y, Z, and it will be null terminated. Right? Yes or no? This is your string, correct? This is the string. Okay, because you can see how would the following C string, this C string is given to you and this is null terminated. So this is terminated by null. So basically this is your C string. This is a string. Okay, so how this string be represented using ASCII in memory? Read this question. This is a very beautiful question, very nice question. See this question. Okay, this string you have, how this string be represented using ASCII in the memory of little Endian system, of little Endian machine. Your system is little Endian with byte addressable memory. Okay, because when you have byte addressable memory, then this Endianness will come into picture. Do you agree with me? When you have byte addressable memory, I told you this, that when you have byte addressable memory, then the concept of Endianness will come into picture. Okay, so you can see here, you have byte addressable memory and your system, your machine is little Endian machine. Now, how this will be represented in the memory? This is what the question is asking. How you will represent this in the main memory? Now, what the question is saying, the bytes are shown. Okay, so forget about this one. Forget, actually some options are given. I don't want to show you the options. Okay, actually what this line is saying, let me tell you what this line is saying. Actually some options are given. Some options are given, but I don't want to give you the options. Okay, so forget about this line. Don't worry. This will make sense once you have the options. Okay, if I give you the options, then this line will make sense. Okay, so don't worry about this statement. This statement, don't worry about this statement, because I did not give you the options. Actually, in this question, there are some options. Okay, now tell me, the ASCII of X is given to you. That is, the ASCII of this is 0x78. The ASCII of this is given to you, that is 0x79. The ASCII of this is 0x7a. Okay, and this is your null. This is 0x00. This is your null. So now tell me the answer. In the little Endian system, what your answer will be? And in the big Endian system, what your answer will be? You tell me the answer for little Endian also, big Endian also. So this is your C string, X, Y, Z, null. Now you tell me how this will be represented in little Endian machine, in big Endian machine. You tell me. In little Endian machine, in big Endian machine. Anyone? In the little Endian machine, in the big Endian machine, how it will be represented? So, in the little Endian, can I say that you will start with the little end? In the little Endian, you will start with the little end. So, you will start with the little end. Yes or no? Then you will put this Z, that is nothing but 7a. Then you will put 7a. Then you will put this Y, which is nothing but 79, and then 78. So can I say this is correct? Can I say this is correct? In the little endian, can I say this is correct? Please tell me, can I say this is correct? Is this correct answer? How many of you are thinking this is correct answer? This is absolutely wrong. Why? This is absolutely wrong. What is the reason? Endianness does not apply to the strings. I told you. Endianness does not apply to the strings. I told you Endian concept, this Endianness, this byte ordering concept does not apply to strings. Yes or no? Please tell me. Did you understand? So this is actually wrong. This is actually wrong. Why? Because if you remember, I told you this concept of Endianness, this Endianness concept does not apply to strings. Yes or no? To strings. This does not apply to strings, structs. Okay. Next, arrays. Is this clear? Please tell me. So remember, the concept of Endianness cannot change the order of these elements. Whatever Endianness you take. See, please understand, whatever Endianness you take, whatever Endianness you consider, whatever Endianness you consider does not matter. The order of these elements will not change. Yes or no? Order of elements in a string cannot change. Order of elements in a string or array or struct cannot change. Cannot change. Is this clear? Please tell me. Yes or no? Okay, so that cannot change. So in the little endian also, in the big endian also, what your answer will be? And you can see the individual items are 1 byte or not. Tell me, the individual items are 1 byte. See, I told you this point that if you have a string, okay, if I give you a string, okay, some string I give you A, B, C, D. If I give you this string, now in this string, this order will not change. Okay, this order will not change in any endianness. Yes or no? This order will not change in any endianness. This order does not change. Does not change in any endianness. Correct? Agree? Okay, in any endianness, this order does not change. Yes or no? Okay, but remember, for every individual element, endianness will apply. Is this clear? Okay, for this endianness will apply. Yes or no? For this, I can say for this primitive data item, endianness will apply. Yes or no? Endianness applies. Endianness applies. If it is multi-byte, yes or no? If it is multi-byte, data, is this clear? Please tell me. Are you getting my point? Okay, so for this also the same thing will happen. For this also, if this is multi-byte data, then endianness will apply. Okay, is this clear? So very simple point, what I'm telling you, that this is a string. Okay, whether you take little endian machine, big endian machine, does not matter. This order of these elements will not change. X, Y, Z, null. This order will not change. And can I say, tell me, this is a 1 byte data or not? Let me know. Please tell me, this is a 1 byte data or not? This is just a 1 byte data item. So because this is just a 1 byte data item, so it will be same in both the endianness. Okay, because this is only 1 byte data item, right? Yes or no? This is just a 1 byte data item. Please tell me, did you understand? So these are just 1 byte data item. And because they are 1 byte data item, so there is no concept of byte ordering. Do you agree with me? If you have only 1 byte, can you do byte ordering? If you have only 1 byte, then can you do byte ordering? No, you cannot do. Yes or no? So very simple. So tell me the final answer now. Tell me the final answer. So in the little endian, what your answer will be? That will be 0x. First you write x. Okay. First you write the ASCII of X, that is 78797A00. So your answer will be 78797A00. This will be your answer in the little endian, and the same answer in the big endian. Please tell me, understood or not? The same answer, the same answer in little endian, big endian, the same answer. Because for string, endianness concept will not apply. Understood? Please tell me. For a string, I told you this, note that this endianness concept only applies to multi-byte primitive data. Okay, this concept, this endianness concept only applies where it will apply? It will apply to multi-byte primitive data item. Okay, and remember, this will not apply to whom? This will not apply to whom? This will not apply to strings, array, and struct. This we have already seen. Okay, so very simple. So you can see that's it. So actually the answer will be 78797A00. I told you that there are options in this question, right? Yes or no? I told you there are some options in this question. These are the options. So you can see this will be the answer in little endian system, in the little endian machine, as well as in big endian machine, as well as in big endian machine. In both the machines, this will be the answer. Okay, understood? Please tell me, did you understand? Let me know. Is this question clear to everyone? So this will be your answer in little endian machine, in big endian machine. In both the machines, this will be the answer. Okay, so this is a beautiful question, right? Students can make mistake. Yes or no? The very common mistake will be this. If you put this, this will be a very common mistake. This will be a very common mistake if you tick this one. The first option, if you tick this, then that will be your common mistake. Okay, so the answer will be actually option D. I hope you understood. Now let's move on. Okay. Now let's solve this ISRO 2020 question. This is a beautiful question in the ISRO exam. Okay, so let's read the question and let's solve it. There are 4 options, A, B, C, D. These are the 4 options in this question. And this is very beautiful question. Let's solve it. So let's solve this ISRO 2020 question. An array. What you have? You have array of 2 byte integers. So tell me what you have. Let me know. You basically have array. This array you have where you have 2 byte integers. Okay, there are 2 byte integers. So here you have 2 byte integer. Here you have 2 byte integer. And here you have 2 byte integer. Is this clear? Okay, so this is your array. This is your array which contains 2 byte integers. Okay, an array is stored. Now this array you are storing. This array we are storing in the big endian machine. Okay, so this array we are storing in the big endian machine. Let's assume this first integer. Okay, just let's call it the first integer. Let's call it I1. Let's call it I2. This is your array. Now we are storing this array in the big endian machine in byte addresses as shown below. Okay, so this is the shown below. What will be the storage pattern in little endian machine? So this is the memory layout in the big endian machine. In the big endian machine, this is how your memory will look like. Is this clear? This is the memory looks like. This is the memory looks like. Okay, is this clear? For array. Looks like for given array. Now, in the little endian machine, how it will look like? Options are already given to you. These are the options A, B, C, D. Tell me the answer. First, you write your answer in the copy, and then I will show you the options. Tell me the answer. This is a beautiful question from the ISRO exam. A very nice question in ISRO 2020. What the question is saying? That in the big endian machine, this is how your memory looks like in the big endian machine for the given array. Okay, you are storing this array. This is array you are storing in the big endian machine. This is how your main memory looks like. Now you tell me, in the little Endian machine, how the memory will look like in the little Endian machine. So have you written your answer? Now I'm showing you the options. These are the options. Tell me. Option A, B, C, D. Tell me quickly. Which is correct? Which of them is correct? All the students are saying option C. Okay, let me check option C or not. Let me check. So you can see, first of all, this is array. You are, remember what you have, your data is array, right? Okay, you have this array. This array you have. Let's assume this is I1, this is I2. Okay, this is your array. Now you tell me whether you take little endian, big endian, can this order change? The order of these elements, can it change? Tell me. This is your array where this is a 2-byte integer. This is a 2-byte integer. This is a 2-byte integer. Okay. Now you tell me, is it possible that their order can change in the little endian, big endian machine? Is it possible their order can change? No. I told you that on the array, this concept of endianness does not apply. This we have already seen. The concept of endianness only applies to multi-byte primitive data items. This does not apply. Please understand. This does not apply to strings, array, or struct. Yes or no? So the concept of endianness cannot change the order of array elements. This is what I can say. Yes or no? So this we have already seen. This note we have already seen that endianness, whatever endianness you take, endianness does not change. Does not change order of array elements. Order of elements in array. In array. Correct? Okay. So this is the main point here. That this is the array. Whatever endianness you take, whatever endianness you take, big endian, little endian, in both the situations, what will happen? Whether you take big endian or whether you take little endian, in both the situations, this order will not change. First I1 will come, then I2 will come. First I1 will come, then I2 will come. Okay, is this clear? Very simple point, right? But you can see this is a multi-byte data. Okay, yes or no? So this is your array, and in this array there are two elements. This I1, this I2, two integers. Now you can see this is 2-byte integer. Okay, because this is a 2-byte integer, so this is your multi-byte primitive data item. Can I say? Please tell me. This is your multi-byte primitive data item. Primitive data item. Yes or no? Similarly, this is also multi-byte primitive data item. This is also 2-byte integer. Okay, which is nothing but multi-byte primitive data item. Okay, so for these, endianness will apply. Multi-byte data item. So I can simply say that for these, for both of them, I can say here endianness applies. Okay, here the endianness will apply. Endianness applies. Simple. Okay, so here endianness will apply. What it means? It means that in the big endian, already it is given to you. Okay, what is given? It is given to you that in the big endian, your photo, the memory photo is already given to you. In the big endian, the memory photo, how it looks like? That looks like, these are the addresses. Okay, 101, 102, 103, 104. These are the addresses. 101, 102, 103, 104. Remember, addresses are going like this. In this order, addresses are put. Now you can see 12, 34, 56, 78. Okay, so in the end, in the big endian, this is already given to you. Now you tell me, what is your array? Can you tell me? Once you have this, then can you find the array? From this, can you write your array? What is your array? Can you write that? Tell me your array. Can you write your array? What is your array that you have stored? So you can see your okay, remember, this is your lowest address. This is your lowest address, right? Okay, so basically this is your, I can say that this is your I1. Okay, this is the I1 and this is your I2. Is this clear? Please tell me. So this is your I1, this is your I2, right? Yes or no? This is your I2. Okay, because You can see this order cannot change. I1, then I2. This order cannot change. The order of array elements cannot change. Whether you take little endian, big endian, whatever you take little endian, you take big endian, this order cannot change. First I1 will be there, then I2 will be there. This order cannot change. Okay, yes or no? So you can see the addresses are going in this order. The addresses are increasing from low to from bottom to top. From bottom to top, addresses are increasing. So you can see this is actually your I1, this is actually your I2. So tell me, what is I1? Because this is big endian. Because this is big endian. So in the big endian, now if I ask you what is I1, then what to do? You can see in the big endian, we start with the big end. This is the big end of I1, right? Can I say this is the big end of I1? Can I say this is big end of I1? Yes or no? This is big end of I1. I1. So I can say your I1 is actually like this. This is your I1. Okay, in the hexadecimal. This is in the hexadecimal. So this is your I1. And what is your I2? Tell me. What is your I2? You can see for I2, remember again, we start with the big end. So this is the big end of I2, right? Can I say this is the big end of I2? This is the big end of I2. So you can see that will be 5678. Okay, is this clear? Please tell me, did you understand? Because in the big endian, what we do, you already know this. In the big endian system, what we'll do, on the lowest address, what you will get? Just tell me this. On the lowest memory address, what you will get? On the lowest memory address, what you will get? You will get the most significant byte. Yes or no? Of data item. Clear? Okay, on the lowest address, you will get most significant byte of the data item. Okay, so you can see here, this is the lowest address. This is the lowest address, 101. So here, this is your most significant byte of I1. Okay, this you can see. This is the most significant byte of I1. Most significant byte of I1. Okay, because I told you that on the lowest address, on the lowest memory address, you will get most significant byte of data item. Okay, similarly here, this is the most significant byte of the data item I2. Okay, is this clear? So very simple. So your array you got. What is your array? Finally, I can say that from here, you can get the array. The array actually, your array is basically this. I1, I2, this is the array. And here you have 1, 2, 3, 4 in the hexadecimal. This is in the hexadecimal. Okay, 5, 6, 7, 8. Now tell me, in the little endian, what your answer will be? In little endian, how the photo will look like? How the memory will look like? In the little endian, 101, these are the addresses, 102, 103, 104. Again, you can notice the order of I1, I2 will not change. The order of I1, I2, that cannot change. Okay, so first you will put I1. So here you will put I1 and here you will put I2. That cannot change. Now let's put the I1. Now I will put the I1. Okay, so when I put I1, then I will start with the little end. So first I will start with the little end, then 1, 2. Okay, yes or no? That's it. So I will start with the little end. Very simple. And similarly here also, I will start with the little end. So 7, 8, and then finally 5, 6. So answer will be 5, 6, 7, 8, 1, 2, 3, 4. This will be your answer. Okay, so which option is correct? Let's see. The answer will be 56, 78, 12, 34. 56, 78, 12, 34. So answer will be option C. That's it. Yes or no? So this is your answer. Option C is the answer. Is this clear? Please tell me. Okay, so this option C, this is the final answer. Okay, so this is a good question. Yes or no? In the ISRO exam, this is a nice question. Okay, tell me what is the most common mistake in this question? Anyone? What is the most common mistake? Most common mistake in this question? Anyone? See, this is the most common mistake that many students, what they will do, they will just change the entire order. Yes or no? They will change the entire order. So 12, 34, 56, 78. They will change the entire order. So if you notice, this is actually the most common mistake. Correct? Yes or no? See, many students, what they will do, they will change the entire order. They will change the entire order. I think this will be the most common mistake. Do you agree with me? Because many students, what they will do, they will just change the entire order. So I think this will be the most common mistake in this question. Okay, but the answer will be option C. This is the correct answer. Okay, let's move on now. Tell me the answer for this question. This is another ISRO exam question, ISRO 2007. Okay, in a big Endian system, the computer stores. The question is asking, if you have a big Endian system, then the computer stores. Which of them is correct? Let me know. The most significant byte, the most significant, see, this means most significant byte. This does not mean most significant bit. This means most significant byte. Byte. Okay, is this clear? This means most significant byte. Similarly, this means least significant byte. Least significant byte. Okay, so the question is asking that in a big Endian system, the most significant byte of data, where that will go? That will go to the lowest memory address. Yeah, that is correct. Option A is correct. Option A is correct. But option D is also correct. The least significant byte of data, that will go to the highest memory address. Yeah, that is also correct. So for this question, answer will be A, D. Okay, both the options are correct. Is this clear? Please tell me. We have already seen this. In the big Endian system, what happens? In the little Endian system, what happens? In the big Endian system, I told you this. You can see, we have already seen. In the little Endian system, what we do? In the little Endian system, just read this. It is given here. See, in the little Endian system, the low order byte at the low address, high order byte at the high address. Yes or no? Okay, similarly, in the big Endian system, the high order byte at the low address and low order byte at the high address. Okay, so this is the answer. Okay, yes or no? In the little Endian, in the big Endian. So remember, in big Endian, what happens? In big Endian system, if you have big Endian system, then in big Endian system, what happens? That the most significant byte, okay, of data, where that will go? Please tell me. Most significant byte of data, where that goes? This means MSB. This means MSB. But remember, this B actually means byte here. This actually means byte. Okay. So tell me, most significant byte of data, where that will go? That will go to the lowest address. That will go to the lowest memory address. That will go to lowest memory address. And where the least significant byte of data will go? That will go to highest memory address. Highest memory address. Okay, very simple. So this is the same thing you can see here. In the big Endian, what we do? The high order byte will go to the low address and low order byte will go to high address. Okay, so most significant byte will go to the lowest address, and least significant byte will go to the highest memory address. Okay, so tell me the answer for this question. That will be option A, D. Okay, in the ISRO, actually, this is MCQ question. So there is a mistake, right, in this question. Actually, this is an MCQ question. In the ISRO exam, you have only MCQ questions. There are no MSQ questions. Okay. So, but actually the correct answer is this. Let me tell you. This A, D, this is the correct answer. You can see this. Already it is given here. We have already seen this. You can see this. Okay. So you can see the answer actually will be option A, D. This is the correct answer. This is the correct answer. But the question maker, maybe the question maker does not know these things. Okay. So maybe, so tell me, if you are in the ISRO exam, which option you will tick? If you are in the ISRO exam, which option you will tick? Anyone? If you are present in the ISRO exam in those 3 hours, which option you will tick? See, it does not matter. Both are correct. Option A, option D, both are correct. If this is a gate exam question, you can challenge it. In the gate exam, they will give you marks for A also, D also, if this is MCQ. Okay, in the gate exam, that is the beauty of gate exam. Let me tell you, if this question comes in the gate exam, and let's assume this is MCQ question, then they will give you marks for option A also. They will give you marks for option D also. Okay, is this clear? But in the ISRO exam, okay, that is, I can say that is not a good exam. Let me tell you, the questions are, I can say many questions are very poorly framed. Okay, very few, very rarely, I can say good questions come in the ISRO exam. ISRO is a, I can say ISRO, if you see the institution is great. Okay, in our, I can say in our country, this is the greatest, I can say one of the very nice institution, but the exam is very poor. The questions are very poor. So you can see here, in this question, answer will be option A, D. Okay, if this is a gate exam question, and let's assume this is MCQ question, then they will give you marks for option A also. They will give you marks for option D also. For both of them, they will give you the marks. And if this is MSQ question, multiple select question, then answer will be AD. Okay, in the ISRO exam, they gave marks for option A only. Okay, in the ISRO exam, because this is MCQ question, they gave, I think they gave the answer for option A. But remember, the correct answer is option A, D. Is this clear? The correct answer, that is option A, D. So your answer will be option A also, option D also. That is the correct answer. You focus on the correct logic. Okay, don't worry about which answer ISRO gave. Don't worry about it. You just focus on the correct logic. What is the correct logic? What is the correct answer? The correct answer is AD. That's it. Okay, now let's move on. Let's solve this question. This is another question from University of New Hampshire on the concept of Endianness. Tell me the answer. This is from University of New Hampshire. A question based on Endianness and 2's complement. Okay, let's see what the answer for this question. What would minus 73 look like as a 32-bit 2's complement integer in memory of big Endian machine? Okay, how it will look like in the memory of big Endian machine? Is this clear? In the memory of big Endian machine, how it will look like? How the minus 73 will look like as a 32-bit 2's complement integer in the memory of big Endian machine? The question is saying the bytes are shown below in increasing memory address order, left to right. Okay, so basically in all these options, the bytes are shown below in increasing memory address order from left to right. So tell me what is the answer. First of all, you convert this minus 73 in 32-bit 2's complement. What it will be? First, let's find out minus 73 in 32 bits. In 32 bits, 2's complement. Okay, so tell me representation. So tell me this minus 73, what it will be in 32 bits 2's complement representation. So how to find that? First you find plus 73. Yes or no? First you find plus 73 in 32 bits 2's complement representation. So what that will be? What this plus 73 will be? Let me know. What is plus 73? See, plus 73, that is actually like this. Okay, you will start with the 0. There will be many zeros. There will be many zeros. Okay, and at some point of time, you will put 1, and then what you will do? So because you want 73, so I can say this will give me, I need 6 space. So this will give me 64. This will give me 2 power 6. That will give me 64, right? Okay. Now I want what? 73. So 73 minus 64. That is, I still need 9. Yes or no? I need 9. So that will be 1001. That will be 9. Okay. The remaining will be 0. So this is your plus 73. Is this clear? Please tell me. This is the plus 73 in 32 bits. These are the 32 bits. Okay. So in 32 bits, your plus 73 is this. So tell me, what will be your minus 73? 32 bits 2's complement representation. Okay. Now you tell me what will be minus 73 in 2's complement representation. What that will be? minus 73. So for that, what you need to do? Very simple. You just go from left to right. See, you just go from left to right until the first one. Until the first one, everything will be same. Okay. The rest, the remaining, you will, what you will do? For the remaining, what you will do? You will complement the remaining. The remaining you will complement. So the remaining you will complement. Okay. 1, 1, and so on 1. Okay. All the remaining will be 1. Like this. So tell me, this will be your minus 73. This will be the minus 73. So in hexadecimal, what I can write it? In hexadecimal, tell me. In the hexadecimal, okay, just go like this and tell me in the hexadecimal. So you can see that is 7. This is 7 in the hexadecimal. What is this in the hexadecimal? That is B. Yes or no? This is B. And what about this? This will be F, right? Because actually this will be 1, 1, 1, 1, and so on. So like this. Okay. So it will be, this will be F. And finally, all will be FF. FF, FF. Okay. So this will be your minus 73. Is this clear? Please tell me. Did you understand this? This is minus 73 in 2's complement. So minus 73, remember? Minus 73 in 2's complement, what that will be? What that will be? So that will be, in hexadecimal I am writing, that will be FF, 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 B7. Correct? Yes or no? Is this clear? Did you understand? So this is your minus 73 in 32 bits 2's complement. Now you tell me, in big endian, what it will look like? In big endian, what it is going to look like? So you can see that this, in big endian, if you have a big endian machine, in big endian machine, what you will do? You will start with the big end. You will start with the big end. So just start with the big end. So in the big endian machine, it will look the same. Okay. In little endian machine, what it will look like? In little endian machine, what it will look like? Remember, addresses are increasing like this. Okay. In this order, addresses are increasing. In the little endian machine, you will start with the little end. You will start with the little end. Okay. So that's it. So tell me which option is correct. So the question is asking for big endian. The answer will be FF, 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 B7. So which option is correct? FF, 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 B7. Which option is correct? None of them is correct, right? Yes or no? None of the options are correct. None. Actually, there is one more option. I did not show you. If you see this original question, there is one more option. None of the above. In this University of Hampshire question, there is none of the above option also. I did not show you. Is this clear? So the answer will be none of the above. Okay. I did not show. Basically, none of them is correct. Not correct, not correct, not correct, not correct, not correct. So the answer actually will be none of the above. You can see here. Okay. Is this clear? But you can see in the big endian answer will be this. In the little endian answer will be this. I hope this point is clear. Okay, correct. So let's move on now. Now let's solve this GATE exam question. GATE 2021. This is another nice question in the GATE exam. In GATE Computer Science 2021, set 2. This is a 2-mark question. You can see. So let's solve it. Can you take your copy pen and solve it? This is a nice question. So let's solve. What this question is saying. Read this question carefully. If the numerical value of a 2-byte unsigned integer, 2 byte means this is multi-byte data, right? Yes or no? This is multi-byte data. So you can see if the numerical value of a 2-byte unsigned integer on a little endian machine is 255 more than that of on a big endian machine, which of the following choices represent the unsigned integer on little endian machine? Okay. See, the question is actually, I can say, if might be confusing. Read the question carefully. What the question is telling you. Just read the question carefully. What this question is telling you. So tell me what this question is saying. The question is saying that the numerical value of a 2-byte unsigned integer. So there is a 2-byte data. Please understand, there is a 2-byte data. Yes or no? Unsigned data. There is a 2-byte data that is unsigned integer. Okay. That is an unsigned integer data. Now, anyway, so you can see there is a 2-byte data. Now, what this question is saying? This question is saying that this is your 2-byte data, whatever data you have. And this data in little Endian machine, this data on little Endian machine, this is actually 255 more than big Endian machine. On big Endian machine. This is what the question is saying. Did you understand? The first line of the question, did you understand? Please tell me. See the question, read the question carefully. Nothing else. This is a very simple question. Just read the question carefully. The question is saying the numerical value of 2-byte unsigned integer. There is a 2-byte data, unsigned data. Now, the numerical value of this data on a little Endian machine is 255 more than that on big Endian machine. So this data that you have on little Endian machine, the numerical value that is 255 more than numerical value on big Endian machine. This is the equation. Is this clear? Now, what is the next line? What is the next line? Which of the following choices, which of them represent the unsigned integer on little Endian machine? Okay, all these options, these are actually on little Endian machine. This is interesting. Tell me. Is this your unsigned data? Is this your data? Is this your data? No. This is your unsigned data on little Endian machine. Is this clear? Please tell me. See, all these options that are given to you, these are unsigned integer on little Endian computer. Did you understand what I'm trying to tell you? So, okay, see, let's see this option A. Focus on this option A, 0x6665. Let's see option A. That is 0x6665. Okay, hexadecimal is given to you. Now, actually, what is this? This is how your data looks on little Endian machine. Yes or no? The question is saying this is how your data looks on a little Endian machine. Agree or not? This is what the question is saying. Read the question carefully. Very simple question. The question is saying which of the following choices, some options are given you, which of the following choices represent the unsigned data on little Endian computer. All these options, these are nothing but your data on little Endian computer. So this option, look at this option A. This is actually what? Tell me. This is what? So this is how your data looks on little Endian machine. Okay, is this clear? So what is your data? What is your unsigned data? So our unsigned data, what is that? Tell me. Let me know. What is our unsigned data? Our 2-byte data, what is that? Our 2-byte unsigned data, what is that? Please tell me. What that will be? Let me know. Let me know. On little Endian machine, it looks like this. Okay, so our data, that actually will be what? That actually will be 6566. Okay, yes or no? Is this clear? Did you understand or did you not understand? Okay, let me explain. See, the question is saying that this is how your data looks on little Endian machine. What it means that on the little Endian machine, okay, let's assume this is address 100, this is address 101. Then tell me, in the little Endian machine, your data is looking like this. Okay, this is how your data is looking on little Endian machine. I can say on little Endian machine, this is how the data on little Endian machine. This is the photo. Okay, this is the photo. Is this clear? Okay. So, is this clear? So tell me, this is how your data looks on the little Endian machine. So what is your data? It simply means what? On the little Endian machine, this is how your data looks. It means what? In the little Endian machine, we start with the little end. So can I say this is the little end of our data? Can I say that this is the little end of our data? Yes or no? Please tell me. Let me know, did you understand? This is the little end of our data. Because in a little Endian machine, on the lower address, we put the little end. So this is the little end of our data. Little end of our data. Okay, because you already know, please understand, you already know in little Endian machine what happens. In little Endian system, what happens? In little Endian system, I can say the most, or I can say on lower address, on lower memory address, what we put? On lower memory address, what we put? Please tell me. On lower address, actually what we put? On the lower memory address, we put the little end. We put the little end means we put little end of our data. Of our data item. Correct. Okay. And what this little end means? Little end, what this means? This means the least significant byte of our data. Least significant byte. Least significant byte of our data item. So on the lower address, actually what we are putting? Okay. On the lower address, this is the lower address. You can see this is the lower address. This is the lower address. So on lower address, what we are putting? We are putting the little end. This 66 is the little end, means this is the least significant byte of our data. This is the least significant byte. You can see this is the least significant byte of our data. Of our data. This is the least significant byte. So our data is basically 666566. I hope you understood. Okay. So remember in option A, what I can say, on little Endian machine, this is how it looks, 6665. But our data will be what? So our data will be what? Our data will be actually 6566. Correct? Yes or no? Our data will be 6566. On big Endian machine, how it will look like? On big Endian machine, how it will look like? Tell me. On big Endian machine, how it will look like? Let me know. On big Endian machine, this data, if you put on the big Endian machine, if you put this data on the big Endian machine, then it will look like 6566. Okay. Now the question is asking, that's it. What the question is asking? The question is asking, let's call it LE and let's call it BE. The question is asking, is this equation satisfied? Is this equation satisfied? Which equation? Is this equation satisfied? Which equation? The question is asking, this LE is equal to 255 plus BE. Is this equation satisfied? Yes or no? Because the question is asking this. See, the question is asking, on little Endian machine, the numerical value is a 255 plus big Endian machine. Okay. So the question, what the question is asking, is this equation satisfied? LE equal to 6255 plus big Endian. Is this satisfied? Okay. What is LE? What is LE? LE is 0x6665. Okay. And what is BE? B is 0x6566. Okay. So you calculate. First you calculate the decimal. In decimal, what it will become? Okay. Tell me. In decimal, what it will become? In decimal, you tell me. In decimal, you tell me what it will become and what it will become. Quickly tell me. In decimal, what they will become. See, this 6665, what it will become in decimal? 6665. First you convert into binary. Let's first convert into binary. In the binary, it will be 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1. This is in the binary. Now you tell me in the decimal what it will become, anyone? Please tell me. In the decimal what it will become. Take the calculator. In the decimal, what it is going to become? 26213, right? Because tell me, what is the weightage of this? What is the weightage of this? Or what you can do? See, you don't have to convert into binary. You don't have to convert into binary. This you can directly convert into decimal. If you have this in the base, this is the base 16, right? 6665 in the base 16. You can directly convert it into decimal. Okay, so in the decimal, what will happen? This 6 multiplied by 16 power 3 plus this 6 multiplied by 16 power 2 plus this 6 multiplied by 16 and plus this is 5 multiplied by 16 power 0. Okay, so that's it. So tell me what it is. If you solve it, what you will get? 6 multiplied by 16 power 3 plus 6 multiplied by 16 power 2 plus 6 multiplied by 16 power 1 plus 5 multiplied by 16 power 0. That will be 26213. Very good. 26213. Okay, what about the next one? What about this one? 6566. What about this one? 6566. Okay, so this is your in the base 16. Now in the base 10, what it will become? In the base 10, very simple. This 6 multiplied by 16 power 3 plus 5 multiplied by 16 power 2 plus 6 multiplied by 16 power 1 plus 6. Okay, so what that will become? That will become 25952. Very good. Okay, 25958. 25958. So this will become. Now tell me, is the equation satisfied? So here you have 26213. Okay, here you have 26213. And here you have 25958. 25958. The equation satisfied or not? Okay, yes, the equation is satisfied, right? Okay, you can see LE is equal to 255 plus BE. Okay, so the equation is satisfied. So because the equation is satisfied, so option A is the answer. I can say option A is correct answer. Option A is correct answer. But this is a MCQ question, MSQ question. Okay, option A is correct answer, but this is MSQ question. Did you understand the question? Did you understand? Now I can say option A is correct. Now you can check the remaining. Let's check the remaining. What about this option B? 0001. You have understood the question. That is the most important part. Okay, once you have understood the question, now you can solve any question. So what the question is saying in the option B, on little Endian machine, what your data looks like? On little Endian machine, your data looks like 0001. So tell me, what is your data? So tell me, what is your data on the little Endian machine? This is your data looks like on the little Endian machine. So what is your data? Your data is actually what? Your data is actually this. On the big Endian machine, what your data will look like? On big Endian machine, if this data you store in the big Endian machine, then what that will look like? That will look like the same. Yes or no? Now, is the equation satisfied? Let's call it LE. Let's call it BE. Is the equation satisfied? This equation. Is this equation satisfied? Is this equation satisfied? Which equation? The equation LE equal to 255 plus BE. This is the equation. Is this equation satisfied? You tell me. This equation is not satisfied. You can check. Okay, you can check. This equation will not be satisfied because what is LE? LE is actually 0x0001. If you convert into decimal, what you will get? If you convert into decimal, what you are going to get? You will get 1 only in the decimal. And what is BE? B is 0x0100. If you convert into decimal, what you will get? If you convert this, then this basically in the decimal, what you will get 1 multiplied by 16 power 2. Okay, so what you will get 256. So actually, if you notice, BE is actually 256, LE is actually 1. So can I say LE is equal to BE plus 255? Can I say? Can I say? No. Correct? Okay. So this option B is not correct. Option B is not correct. I can simply say that option B is gone. Okay. What about option C? What about option C? 4243. Let's check it. 4243. Option C. On the Little Endian machine, how your data looks like? On Little Endian machine, your data is looking like 4243, right? Yes or no? 4243. On the Little Endian machine, this is, remember, on Little Endian machine, this is how your data looks like. 4243. Now you tell me. So what is your data? What is your data? Let me know. On the Little Endian machine, this is how your data looks. So what is your data? Your data is actually 4342. On the Big Endian machine, what your data will look like? On Big Endian machine, your data will look like what? Your data will look like 4342. Let's call it LE. Let's call it BE. Now tell me, convert them into decimal and tell me, is this equation satisfied? LE equal to BE plus 255. Is this equation satisfied? This equation, I think it will not be satisfied, right? Yes or no? Okay. Because you can convert into in decimal, what it will become? In decimal, what it will become? Tell me. This LE, that is 4243. Okay. So in decimal, what it will become? It will become very simple. 4 multiplied by 16 power 3 plus 2 multiplied by 16 power 2 plus 4 multiplied by 16 power 1 plus 3 multiplied by 16 power 0. Okay. So you tell me, if you calculate this value, then you will get 16963. 16963 in the decimal. What about BE? What about BE? That is 4342. What about that in the decimal? In the decimal, that is 17218. Okay, so this equation is clearly not satisfied. LE equal to 255 plus BE. This equation is not satisfied. So this option is not correct. Okay, option A is correct, option B not correct, option C not correct. Finally, what about option D? Option D will be correct. Option D, you can check option D, that is 0100. Okay, let's just quickly check the option D. What option D is? On Little Endian machine, what your data looks like? Your data looks like 0100. 0100. Yes or no? On the Little Endian machine. So what is your data? So what is your data? Your data is actually 0001. So on Big Endian machine, what is your data look like? On the Big Endian machine, what your data looks like? On the Big Endian machine, your data looks like this. Okay. Now, if you convert it in, let's call it LE. Let's call it BE. So what is LE? LE is 0x0100. If you convert into decimal, what you will get? You will get 256. Okay. What is BE? What is BE? B is 0x0001. If you convert into decimal, you will get 1. So this equation is satisfied. LE equal to 255 plus BE. This equation is satisfied. Yes or no? So this is correct. So finally answer will be AD. So for this question, the answer will be what? The answer will be AD. Did you understand? Please tell me. Let me know. What is the most common mistake in this question? What is the most common mistake in this question? Students can make a mistake of interpretation. Yes or no? In this question, you can make a mistake during interpretation. What are these options? Are these options your data, or these options are data on the little Endian computer? Yes or no? Yes or no? Is this clear? See, most common mistake is students will take this as a data. Okay, yes or no? This is the most common mistake, that students will take this as a data, Okay, they will think that this is the data. But actually, what is this? This is on the little Endian computer how the data looks like. On the little Endian computer, how your data looks like. Okay, is this clear? Did you understand this question? Please tell me. Please tell me, did you clearly understand this question? What this question is saying? And the answer is option A, D. Okay, so very simple, right? So the answer, final answer will be option A, D. Now let's move on. Tell me the answer for these three questions quickly. These are standard questions from university, from standard university. Okay. So quickly tell me the answers for these questions. Little Endian versus big Endian comes into play. When it will come into play? Little Endian, big Endian. These concepts, basically the concept of byte ordering. When the concept of byte ordering comes into play, little Endian versus big Endian, that simply means byte ordering, right? That means byte ordering. So when this byte ordering will come into play? This byte ordering will come into play when your memory is byte addressable and word contains multiple bytes. Yes or no? Agree with me? Correct or not? So option B, yes or no? Because byte ordering, when the byte ordering will come into picture? Byte ordering comes into picture when? Byte ordering when your multi-byte data. When your multi-byte data and byte addressable memory Correct or not? Yes or no? So answer will be option B. What about the next question? Please tell me. In little Endian system, the big end of binary integer, where that will go? In little Endian system, the little end will come first. Yes or no? In the little Endian system, the little end will come first. So the big Endian will come last. Option B. Yes or no? Because in the little Endian system, little end comes first. Little end comes first. Okay, so the big end will come last. What about the next? Which is better way to address memory? Which is better, little Endian or big Endian? Which is better? Tell me. Little Endian, big Endian, which is better? I told you none of them is better. In some situation, little Endian is good. In some situation, big Endian is good. But overall, no one is better. Okay, means basically we cannot compare. We cannot say that one of them is better than other. Okay, yes or no? I told you. Remember, some systems use little Endian, some systems use big Endian. I told you. Intel uses little Endian, right? Little Endian used by Intel. Correct? I told you this. Intel uses little Endian and big Endian used by Motorola. Correct? Agree? So remember, some systems they use little Endian, some systems they use big Endian, but none of them is better. Okay, so these are the three questions we have done. Tell me the answer for this question also. This question is also from Standard University. Why is it necessary to know whether a computer is big Endian or little Endian? Means basically when little Endian, big Endian matters for a programmer. Tell me. In which situation little Endian, big Endian matters to you? The question is, see, read the question, what the question is asking. The question is asking, in which situation little Endian, big Endian matters? In which situation does it matter whether your system is little Endian or big Endian? Tell me. What is the answer? The answer is C. Because some programs write integers to memory in certain order. This does not matter. Yes or no? Tell me, as a programmer, did you ever worry about big Endian, little Endian? Did you ever worry about little Endian, big Endian as a programmer? You never worry about little Endian, big Endian. Yes or no? So some programs write integers to memory in certain order. Does not matter. Okay. Here actually we don't care. Here we don't care about Endianness. Here we don't care about Endianness. Who will take care of this? Tell me, who will take care of this? I told you that you don't have to, as a programmer, you don't have to worry about Endianness because it will be taken care for you. Okay, software plus hardware, they will take care for you. Compiler, assembler, hardware, okay, all of them will take care for you. So here you don't have to worry. As a programmer, when do you have to worry about Endianness? I told you this. As a programmer, as a coder, when do you have to worry about Endianness? When the Endianness will affect you. When Endianness will affect your answer, tell me. The reason I told you, when you store the data in a different way and access that data in a different way, yes or no? You are storing the data in the integer format and you are accessing the same data in the character format, yes or no? Is this clear? You store the data as an integer, but you are accessing the same data as a character. In this situation, Endianness will matter, yes or no? So as a programmer, when Endianness matters, when different Endianness can give you different answer, when it will happen? It will happen when you access the data in different amount than you have stored it. Okay, you are storing the integer data, but you are accessing the character data. Okay, you store the variable. Let's assume you have some variable I. You store the variable as an integer, but you are accessing the variable, the same variable you are accessing as a character. In this situation, Endianness matters. I told you this. And what was the another situation? The another situation was when you transfer files or data between different computers over a network. So here Endianness will matter. Okay. And here Endianness does not matter. Okay. Yes or no? So very simple. So for this question, the answer will be option C. Did you understand this? Let me know. I told you that there are two situations. In two situations, the Endianness matters. The different Endianness, you have to take care about Endianness. Okay, yes or no? There are two situations. The first situation is when you share the data over a network, when you are transferring the data from one computer to another computer over a network, then you have to take care of Endianness. And the another reason is you are accessing the data in different amounts than you stored it. You are storing the variable as an integer, but you are accessing the same variable as a character. In this type of situation, Endianness will matter. Okay. So anyway, so for this question, the answer will be option C. That's it. This is your chapter. A lot of questions we have done, right? I don't think that they can ask you any question out of our lecture. What do you think? What do you feel? All the questions that we have seen, do you think they can ask you something out of our lecture? I don't think. Okay, whatever they will ask in the GATE exam, in any exam, whatever question they ask you, whether they ask you complicated question, tricky question, easy question, whatever they ask you, that will definitely be, I can say, coming from our lectures. Okay, we have covered everything. Okay, all the type of questions we have covered. The GATE question, ISRO question, Washington University question, New Hampshire University question, everything we have covered. Okay, so that's it. So this is your chapter. Please tell me, did you understand? Whatever question comes in the GATE exam in future, are you confident that you can solve it in the GATE exam in future from little Endian, big Endian, based on this byte ordering concept? Whatever question comes, are you confident that yes, you will be able to solve? Okay. So just pray that a question comes, yes or no? A good quality, a nice tricky question should come in the GATE exam that will benefit you. Okay, just pray that some tricky, some complicated question from this topic comes in the GATE exam next year. Okay. If it comes, then it will benefit you. Okay. So thank you, everyone. So did you understand this topic clearly? Please let me know in the comments. Okay. Okay. Thank you, everyone. See you in the next lecture tomorrow.